For nuclear energy, we're going to be talking about using uranium-235 as a source, as a fuel, all right? So we've talked about fission reactions releasing large amounts of energy, as well as fusion reactions doing this as well. But it is much easier to create a fission chain reaction and to control it than it is for fusion. So we use uranium-235, all right, to create a controlled chain reaction of fission. So the process follows, all right, that if you bombard or unstable nucleus absorbs a slow enough neutron, a special type of neutron, all right, that we're going to talk about a little bit later, it will end up being able to fission rather quickly and split into two small nuclei and a couple of extra neutrons. So the neutrons, since they're neutral, okay, they are not repelled by the nucleus, and so they are much more easily absorbed at the right speed. All right? So, what happens, all right, is that we have the rest mass, all right, the products, it's going to be less than that of the reactants, all right? So what we see is that some of that is converted, mass is converted into energy, and we see it, again, in the form of kinetic energy of the daughter particles, all right? And this is just like when we learned about fission. So a particular nuclear reactor, right, we could say, for a practice problem here, we use uranium-235 as a source of fuel. And when a particular nucleus of uranium-235 is going to absorb a neutron, we'll see the following reaction take place. There are many different possible reactions that can happen, but we're going to use this one here. So the first thing we need to answer is how many neutrons are produced in excess in addition to the split uranium-235 nucleus into the xenon and strontium, all right? And what we end up seeing, okay, if we add up the total number of neutrons, all right, that are in this equation, we will end up finding that there are two that need to be over here. So the way I did that is I just added up the total mass numbers on both sides. Should get out to 236, and over here with 144.90 gives us 234. All right, so we have to have two neutrons over here. All right, so now we can use that information and calculate the energy that's been released. If you just find the mass defect for this, all right, it's just going to be the mass of the reactants minus the mass of the product. So we'll have the mass of the uranium plus the mass of the single neutron, all right, minus the mass of the xenon plus the mass of the strontium here in this quantity, oops, SR, and the mass of the two neutrons. All right, we can solve for this, and what we end up with using these masses over here is 180 mega electron volts per c squared. Remember, this is a unit of mass, so when we look at the energy that's been released, we have to plug this in as the mass, and these c squareds nicely cancel out. Yes, you do need to show that. All right, so this is the energy released in a single fission reaction with uranium-235 making these two products. All right, so what happens then, okay, is that we want to compare what the energy density really is here. All right, so let's just say, all right, that for coal, okay, we're going to say that every atom of carbon in coal combusts cleanly, okay, which basically means if you burn it with oxygen, it's going to form CO2, and whatever hydrogen is in there is going to form H2O. Okay, so this is a very, very rough, okay, general calculation just to get the idea across here. But based on the fact that we'll say if every carbon-12 atom burns, all right, and in that process it's going to make 4 electron volts worth of energy in that combustion process, and if every single uranium-235 nucleus fissions, each one of those will make 180 mega electron volts, all right? So if we want to figure out what the energy density of each of these are, compare them, right? For carbon, what we'll see, all right, is that the energy density is going to be 4 electron volts per 12 unified atomic mass units approximately, all right? And so, or per nucleon, if we want to do it that way, actually, that would go that way, all right? And what we get here is that we have 1/3 of an electron volt per nucleon. When we compare this to uranium, all right, again, very, very rough calculation, we have 180 mega electron volts, all right, per 235 nucleons. Okay, so we see here that the ratio of their energy densities already, right, is going to be incredibly high in favor of uranium. So we take that ratio, just going to be taking this 7.66 times 10 to the 5th, all right, divided by 1/3, and what we end up with here is 2.3 times 10 to the 6th, all right, as the ratio. If you look at the table there in the beginning of the chapter, right, for coal, I believe the energy density was 32.5 megajoules per kilogram, and for uranium, I think in that table it said it was 90 terajoules per kilogram. Right, if you take a ratio of these two, all right, that ends up being 2.8 times 10 to the 6th. So you really get a close number there, okay, in terms of the ratios. So what does this suggest then about uranium compared to fossil fuels? Well, obviously, okay, you don't need as much, all right, to do the same amount of work. So in other words, I mean, you need 3 million times less uranium than you need coal in order to generate the same amount of electricity, which is an astounding figure, all right? So let's talk more about this process of using nuclear fuel, all right? You have there on your page, all right, talks about uranium-238 versus uranium-235. 238 is the most abundant source, so what needs to happen is a process called fuel enrichment, okay, to get the uranium up to a concentration at which it is easier to sustain a chain reaction, all right? So uranium-235 is very rare, 238 is very abundant, all right? And what we need to do is to increase the concentration. So the reason for that, okay, is that we need to have a sustained chain reaction. In other words, what happens is that we have neutrons released from one fission, all right, are going to go on and initiate further chain reactions, all right? If you don't have enough of a concentration of uranium, or if there aren't enough neutrons, you're not going to have this chain reaction. If you have too many neutrons or too much uranium around, we have an uncontrolled nuclear reaction, all right? And that is going to end up being a bomb. That's what we're used to knowing as nuclear weapons. If we can control it, though, and get the rate to be constant, we have nuclear power. So really, that's just the difference here between these two chain reactions. Okay? So in order for that to happen, okay, in order for uranium-235 nucleus to split, it must absorb what's known as a thermal neutron. Okay, so this is a free neutron that is going to be slowed down, all right, by a substance we call moderator. So it collides through this substance. So, you know, when that uranium-235 nucleus first absorbs a neutron and emits those excess neutrons, they're typically traveling at a pretty high velocity, okay? So the reason why it needs to be slowed down is that it needs to have enough time, all right, for the strong nuclear force to actually have a chance to possibly hook it in there into the nucleus, okay? So it's been slowed down after fission by a moderator. Okay, so a thermal neutron is much more readily absorbed. Okay, so that's one piece that you do need to be able to understand for this unit here. So that page there talks about the process of fuel enrichment. You should just read over it just to see, you know, how it happens. You don't need to know exactly how it happens, but you do need to know that it brings the concentration of uranium up from 0.7% up to 3 to 5% of the total amount. And that's exactly what you want to have for nuclear fuel. Obviously, a disadvantage that if you keep doing this process and get it to a really high level, and not something like 90% would be that required for a nuclear weapon. All right. There's one more vocab word here that you guys need to know. So the critical mass is the minimum when you enrich this when you enrich uranium. Okay, it's the minimum mass that you need present, all right, for a self-sustaining chain reaction of fission. So, I mean, literally, what's happening is that you have all of these uranium nuclei breaking apart, spitting out pieces of themselves, and those pieces being absorbed by the next set of nuclei, breaking apart, and just repeating the process over and over. And if there's there's enough uranium present, the density is high enough that that's going to be your critical mass really. That's going to allow you to keep having a chain reaction. All right. So let's talk about how exactly we get to generate electricity. Okay, and what happens. What we do, all right, is we have the fuel rods, all right, in some sort of substance, okay, typically a moderator, all right, that helps to slow down the neutrons. And these fuel rods are also surrounded by control rods, okay. So the control rods help to basically absorb excess neutrons to prevent the reaction, the chain reaction from going too fast. So you can actually use the control rods like a gas pedal or brake, if you want to think of it like that, okay, for the chain reaction. So you have the control rods that slow down or speed up the reaction if you push them in or pull them out. You have the moderator, which is some substance. Okay, it could be heavy water, it could be graphite. That's going to be the stuff that will slow down those neutrons so that they can be absorbed by the other uranium. And so, yeah, that's like the main part of the core. So we start out, okay, with this nuclear energy, right? That conversion of mass into energy, all right? And from there, we go to the kinetic energy of the daughter particles, okay? And that's going to heat up water. So think of it as going to thermal energy of water, just, obviously the kinetic energy too in some way, all right? And this is just like our coal plant now, from the rest of the way out here. We go to kinetic energy of the turbine, all right? And that generator, which then we go generates electrical energy, and we send that out on the grid. Okay? If we sketch a Sankey diagram for that, all right? You had, it would be good practice actually if you guys did this, but we'll go over in class. 100% incoming, we can say uranium fissionable energy into uranium-235. About 48% is waste heat. Okay. Remaining energy in the fuel rods is about 20. Let's see, 27%. Okay, so this is remaining in the fuel rods. Okay, and what we end up with is about 25% electricity. Okay, and that's about it. So we can do some calculations here to figure out how much nuclear fuel we would need to run a power plant, and I'm going to do that in the next video.